Hello students, good morning all of you. So this is the fourth lecture of the Oscillations chapter, and today in this chapter and in this video I want to explain very important questions which are very important for the board examinations. So both AP and Telangana. So damn sure definite questions for the IPE examinations, which is weightage of 10 marks. One it is 8 marks question and other it is the 2 marks questions. Okay, so get ready guys, you have to take your notebook and the pen, start the writing, and what I am teaching here is very important. Please focus on the board, and if you have any doubts please ask me in the comment section. So you should follow our channel regularly and it is very useful to you, and who does not follows the online classes, you should follow our channel. You will get definitely more and more ideas for getting the good marks in the physics examinations. Okay, so let us start our topic. Yes, this is the chapter, it is oscillations. So in our previous videos we are discussing about the oscillation patterns of the motion of the particles in various positions, and also we have to discuss the time period of the particles, how we can find the mean position and mean position to extreme, and on the way what they had to be having the time period. So that is also we are completed, and one more we are completed, that was nothing but the circular motion. In case of circular motion, the particles are moving in simple harmonic motion. So but today we are discussing about only 8 marks, only essay type questions, 8 marks questions, 8 marks questions. So this is the definite question for the IPE examinations. Okay, so here there are 3 questions are there in this chapter. There are 3 questions are there. If you have focus on 2 questions and you will get 1 question. Okay, just to focus on 2 questions. Okay, and you will get, definitely will get 1 question. That is for 8 marks. First question. So what is the first question? So that is projection of particle. Projection of particle in a uniform circular motion. Uniform circular motion. Uniform circular motion. Okay. So the projection of the particle is in simple harmonic motion. Definitely it is in simple harmonic motion. How it is in simple harmonic motion, let us describe. Right? So let us assume a particle which is in a circular motion. Which is in a circular motion. This is the origin which can having the x dash is the diameter of this circle. X dash is the diameter. X dash is the diameter. That is nothing but this is the x and this is x dash. And this is the center point, that is the origin, which is denoted by the O. And here this is the y dash. This is the y dash and this is phi along with the y axis. Here there is a particle. Here there is a particle is performing in anti-clockwise direction, which is moving in the anti-clockwise direction. So the particle is at a time t is equal to 0. The particle is at position at this point. And after t is equal to time t, then the particle is at point P. That is the particle name P, and here the position it is at this point. Okay. Now the angular displacement of the particle here, this is the theta. Theta is the angular displacement of the particle. The velocity of the angular velocity of the particle is omega. The angular velocity of the particle is omega. Now we have to doing what is the displacement of the particle from the x-axis. What is the displacement of the particle from the x-axis? Here we have to write a foot of the point P. So this is the foot of the point P, which is coincide at the point N. So the distance between O to N, it is the x. Along with the x-axis, the displacement, it is the x here. And let it be write the foot of the point P on y-axis. So this is the point, whereas let it be M. Okay, so from O to M, it is the displacement of the particle along with the y-axis. Along with the y-axis. Now here, this is the theta. Here, this is the theta. So here, there are two right angle triangles are there. OPN and OPM. OPM. From these two right angle triangles, we have to describe the displacement of the particle and the velocity of the particle and also the acceleration of the particle. If the acceleration of the particle is directly proportional to its displacement and in negative in nature, then we can confirm that the particle should be maintaining simple harmonic motion. So this is the basic theory to confirm the particle which is in simple harmonic motion. Clear? So now our aim is to find the acceleration of this particle. Acceleration of this particle. So to find the acceleration, before that we have to need its displacement and its velocity. From that, by the displacement we can getting the velocity. By the change of the velocity, the rate of change of velocity, we can get the acceleration. Okay. Now let us see. So from triangle OPN, from right angle triangle OPN, we can derive that. So whereas this is the displacement along with the x-axis, where it ON, it is the x. So we can find the displacement. For getting the displacement, along x-axis, therefore cos theta it is equal, because of the x displacement is nothing but adjacent of the theta. So then we have to write that cos theta it is equal adjacent by hypotenuse. Adjacent it is equal ON by hypotenuse, it is the OP. So ON it is the x, where OP can be measured the displacement, the maximum displacement of the particle from its origin. That is nothing but its amplitude. The simple harmonic oscillator, the maximum displacement traveled by the particle is nothing but its amplitude. So let's write it is x by A. So x is the displacement of the particle, it is x is equal A cos theta. So here theta is the angular displacement. So from this one we can write that the angular displacement theta it is equal to angular velocity into time. Theta it is equal omega t. Okay, so already you know that the angular velocity it is equal and rate of change of angular displacement, that is the angular velocity. Then we can write that theta is equal omega into t. So let's write that x is equal A cos, where theta nothing but omega t. So this is the displacement of the particle which is performing uniform circular motion. So this is the equation 1. Our aim is to getting its acceleration. So for getting the acceleration, we need to find its velocity. We have to derivate above equation with respect to t. d by dt, derivate with respect time on both sides. Derivate with respect time on both sides. Therefore, d by dt of x it is equal to d by dt of A cos omega t. So it is nothing but dx by dt, where dx by dt it is equal to its velocity. So the rate of change of displacement, the time will be, so displacement by time it will be gives us the velocity. So it is equal, A should be a common letter, that is constant. It is A into d by dt of cos omega t. cos omega t. The derivation of cos omega t, it is the derivation of cos omega t, it is the sin omega t. A into sin omega t, the omega t should be derivated by with respect to time, then we can get the omega. So therefore velocity v is equal a into omega, v is equal to a omega sin omega t, a omega sin omega t. So this is the velocity of the particle which is performing uniform circular motion. Right. So for getting the acceleration, we have to again derive with respect to time on both sides this equation 2. So then we can get its acceleration. Then we can get the acceleration of the particle which is performing uniform circular motion. Now let us write. So here dv by dt, it is equal to d by dt of, what is that here? A omega sin omega t. A omega sin omega t. Because of that is the equation of the velocity of the particle which is in uniform circular motion. Clear? So the rate of change of velocity gives us the acceleration, which should be written as A. A omega, it is equal constant, and then you can write d by dt of sin omega t. It will gives us the minus cos omega t. The derivation of the sin omega t, it is equal minus cos omega t, and omega t derivated by the respect time, then we can get the omega. So omega into omega, omega square, minus should be written as minus a omega square cos omega t, minus a omega square cos omega t. So this is the acceleration of the particle. So from this equation, so let us write so where x is equal a cos omega t, it is from the equation of 1, we can write that x is equal a cos omega t. A into cos omega t, it is the x value. So put it here, a is equal minus omega square into x. A is equal minus omega square into x. From equation 1. Because of x is equal a cos omega t. A into cos omega t, it is equal x. Therefore, we have to write minus omega square into x. From this equation, we can write that a proportional minus x. A proportional minus x. So this can be said that the acceleration of the particle is directly proportional to its displacement, and also in negative in nature. If acceleration is positive, the displacement is negative. If the acceleration is negative, the displacement is positive. Okay, so this equation said to be the projection of a particle which is in uniform circular motion is in simple harmonic motion. Okay, so this is very, very important question. So this is the one of the 8 marks question. Very, very important. So all of you take it as screenshot and you should write. Very important. Okay. So and finally you have to write here from above equation we can say that the acceleration of the particle is directly proportional to the displacement of the particle which is performing uniform circular motion and also in negative nature. Hence we can say that the projection of a particle in a uniform circular motion is in simple harmonic motion. Clear? Okay, so this diagram is also very important. Okay, note it all of you. Right. So now coming to the second question. So what is the second question here? The second question it is here the second question, simple pendulum. Simple pendulum. Simple. The pendulum which is simple. Of course, the answer is also very simple. The description also very simple. Okay, simple pendulum. The question it is, define SHM. Define SHM. Show that the motion of the simple pendulum is in is in SHM, and derive its time period. Derive its time period. What is seconds pendulum? This is the purely, the question belongs to board examinations. That is IPE, Intermediate Public Examinations. Okay. What is seconds pendulum? Right. So how we can, first we have to define the simple harmonic motion. The simple harmonic motion, it is defined that the particle must be having the to and fro motion. The acceleration of the particle is always towards its mean position, and also the acceleration of the particle is directly proportional to its displacement and in negative in nature. So these qualities are belongs to the simple harmonic motion. Right. And coming to the simple pendulum. So what is a simple pendulum? A simple pendulum is an arrangement of, so one of the inextensible thread, we have to take one inextensible thread which is fixed end, which can be fixed to the one of the end. This is the rigid support which we have to fix as the one of the end of the thread. This thread has a inextensible and massless thread. So the other end should be attached a bob, a spherical metal bob. So this arrangement is known as the simple pendulum. So here, this is the center of the bob. The distance between suspended point, this is the suspended point. The distance between suspended point and to the center of the bob is called length of the pendulum. The distance between suspended point and to the center of the bob. Okay, this thread has massless and inextensible and massless. Inextensible and massless thread. One of the end is fixed to the rigid support and other end is attached to the metal spherical bob. Okay, this arrangement is known as the simple pendulum. The distance between the suspended point and to the center of the bob, not it is a bottom of the, this is the bottom. The distance between suspended point and to the center of the bob is called length of the pendulum. So length of the pendulum L, it is, we have to take in the distance from the suspended point to the center of the bob. Okay, and now we have to derive its time period. Okay, simple, the motion of the pendulum is in SHM, and also find its time period. So to derive the simple harmonic motion, we have to find its acceleration, and we have to prove the acceleration will be always directly proportional to its displacement and also in negative nature. So is it possible or not? Let us see. Right. So whenever we have to, so here this is the mean position of the bob at equilibrium position or mean position. If there is no motion, it is at rest, it is the equilibrium position. It has the angle theta is equal 0. So here there is no motion of the particle, hence the theta is equal 0. Now we have to move this bob aside, and leave it. Then it will be oscillates on the planar motion. So it will be goes to the extreme and moves towards the mean position and goes to the extreme and moves back towards the mean position and goes upward. So this is the motion of the particle. So now let us write, we have to pull a side of the bob. So with some angle theta. We have to pull a bob with some angle theta. So this is the bob here, right? This is the bob, and here the angle made by this, it is the angular displacement. Angular displacement. Here the distance moved by the particle, it is x. Okay, so this is the motion. And now whenever it has been maintaining theta angle, so here at first the weight of the bob mg will be acting in downwards, and the tension will be acting in upward direction. Tension T should be acting in upwards. The weight of the bob should be acting in downwards. These two are balancing to each other. And whenever we have to pull aside with some angle theta, with an angular displacement here, so then the mg should be, that is the net weight should be divided into two components. So that is the mg should divides in two components, that is, first one, horizontal component, that is nothing but mg cos theta, which is acting towards the thread, which is acting towards the massless inextensible thread. So this is the mg cos theta. It will be balancing the tensional force. It is balancing the tensional force. And the second one, it is the vertical component. So whereas the vertical component is equal to mg sin theta, which is used to as restoring force, mg sin theta. So this mg sin theta force should be moves back to the bob from extreme to its mean position. It will always use it to move back to the particle towards its mean position. So mean position వైపుకు mg sin theta తీసుకోవడానికి ఎప్పుడు ట్రై చేస్తుంది, that is the restoring force also. That is nothing but restoring force. We have to say that is the restoring force. So here it will be moving this type of oscillation. So this is the major key role we have to derive about the acceleration. Okay, right. So here the restoring force. So already I said that mg cos theta is balancing the tensional force in a string, and mg sin theta is used as restoring force. So this is restoring. So this is restoring force, and this is balancing force. Clear? This is balancing. Simple. Now the restoring force F is equal to minus mg sin theta. Why we need to take as minus? So because of restoring force always opposite to the external force. So we have to take this in this side, but it will be moves in opposite direction. So hence we have to take it is negative sign. So where F is equal from Newton's second law, F is equal to ma, you can write here ma it is equal minus mg sin theta, where m gets cancelled, a is equal minus g sin theta. We have to find acceleration. If acceleration is directly proportional to its displacement and in opposite direction, then you have to say it is in simple harmonic motion, right? So here if theta is very small, so here the simple harmonic motions are possible only small amplitude of the bob, small amplitudes. So it is small amplitude. So it is, if it is a bigger amplitude, it will not be moves in the planar motions, it will be rotating. So for small amplitude only it has maintaining simple harmonic. So for small amplitude has small angle. So if theta is very small, then we can write that Sin theta is equal theta, right? So then we have to substitute here. A is equal minus G into theta. So here sin theta is replaced by the theta. Now we have to find the value of theta. What is the value of theta? How we can find the value of theta? So let us suppose if your bob is moving in vertical circular motion, so as in this direction, right? So then this part should be known as arc length. X should be known as the arc length. So the angle it is equal, theta is the angle also. Theta is nothing but angle here. The angle should be found out by the theta is equal angle arc length by radius. So what is the arc length here? It is x. What is radius here? So for getting the circular motion, so this is the radius. How much here it is? L. L is the radius. So for getting the oscillation, one of the circular motion, so this will be this distance is known as the radius, that is nothing but length. Length should be used as radius and x it is the arc length, where x by L, theta is equal to x by L. Simple, theta is equal to x by L. So just you have to write that, where theta is equal to x by L, so we have to derive the acceleration. Okay, so let us substitute here. What is that here? Whereas A it is equal minus G into x by L, theta is replacing by x by L. A it is equal minus G by L into x, minus G by L into x. X it is the displacement. Okay, if G by L, so this is the equation finally we got. This can be comparatively, whereas minus omega square x, this is the basic equation of the simple harmonic motion. So here omega square is the constant, x is the displacement. Here G by L is the constant, x is the displacement. Okay, so hence we have to say that from this equation you can write that A proportional minus x. A proportional minus x, it will be gives us the definition of the simple harmonic motion. Clear? So the motion of the pendulum is in simple harmonic motion. Yes, the motion of the pendulum is in simple harmonic motion. And now we have to find its time period. How we can find the time period? So from these two equations we can write that omega square it is equal to the G by L. Omega square is equal to the G by L. Okay. So how we can find the time period? Let us see. So all of you, let us write. Note it, all of you. And we have to take the screenshot. Right. So now here we have to find the, what is that? Time period. How we can find the time period? So from these two equations you can write that omega square it is equal G by L. Omega square is equal G by L, where omega it is equal under root of G by L. Under root of G by L, G it is the acceleration, G it is the acceleration, and L it is length. L is equal length. Right. So now time period T is equal to 2 pi by omega. 2 pi by omega, where omega is equal under root G by L. So it is equal to 2 pi by under root of G by L. It should be written as 2 pi into under root of L by G. So this is the time period of the simple pendulum. Time period of the simple pendulum. Okay. So now what is seconds pendulum? What is seconds pendulum? The time period of the pendulum, capital T is equal to 2 seconds. Capital T is 2 seconds. Whose time period of the pendulum is 2 seconds, then it will be said to be seconds pendulum. The time period of the pendulum is 2 seconds, then it can said to be seconds pendulum. Okay. So it means at how much length it has to take the 2 second time to complete the one oscillation. Time period is meaning that to complete the time taken to complete the one oscillation, it is 2 seconds. ఒక కంప్లీట్ ఆసిలేషన్ చేయడానికి 2 సెకండ్ల టైం పట్టేటువంటి ఏ పెండులం అయినా సరే, దట్ ఈస్ ద సెకండ్స్ పెండులం. వాట్ ఈస్ సెకండ్స్ పెండులం హియర్? Whose time period is 2 seconds equal to 2 seconds, then it is called seconds pendulum. So for getting the time period 2 seconds, how much it has the length? We have to find the length of the seconds pendulum. The length of the seconds pendulum, literally it is 1 meter, 1 meter, or it is 100 centimeter, or it is 100 centimeter. This is the length of the seconds pendulum. A pendulum which can has the 100 centimeter of length will be time taken to complete one oscillation is 2 seconds. Is 2 seconds. That is the seconds pendulum. Okay, clear? So this is the clear idea about the simple pendulum. Okay. And now let us see the third question, which is very important for the IPE examinations. These two questions are very important, definite questions for the board examinations. You must follow. So from these two questions you will get one question for 8 marks of weightage. Okay. And now we are learning one more question, which is the total energy of the simple harmonic oscillator. Total energy of a simple harmonic oscillator. Total energy of a simple harmonic oscillator. Total energy of a simple harmonic oscillator. Before going to learn, we can discussing about the law of conservation of energy. So the simple harmonic oscillator as obeys the law of conservation of energy. Is it right or not? So I can say the simple harmonic oscillator must be obeys the law of conservation of energy. A particle which is moving in the simple harmonic, which can be shows the simple harmonic motion, that must be having at any point it has the same energy. It has the same total energy. The total energy at all the points of a simple harmonic oscillator remains the same. Hence we can say the particle of a SHM should obey the law of conservation of energy. Law of conservation of energy. Of course, the energy should be changes one form to another. It is meaning that potential energy to kinetic energy and kinetic energy to potential energy. But still the total energy will be the same, remains same. So for in case of a simple harmonic particle, a particle which is in simple harmonic motion, it has maintaining the mean position, and that is nothing but the equilibrium position, and also in the extreme position, and also in another extreme position. So the total energy will be find out by the for getting the potential energy at the same point, and also at that point kinetic energy, we will be added these two, we can get the total energy at the same point. For suppose at mean position, how much potential energy has the particle, and also how much kinetic energy has the particle, and then we have to add it these potential energy and kinetic energy, and we will get the total energy of the particle which is in the mean position. And similarly we have to find the extreme position. Okay. So now we have to find the total energy. Total energy, it is meaning that the meaning of total energy, it is here. The meaning of total energy, it is equal. P is equal potential energy plus kinetic energy. Potential energy plus kinetic energy. First, suppose we have to take a simple harmonic oscillator. So this is the particle which is in mean position. So this is the point which is extreme. So this is the another extreme. So where x is equal displacement of the particle at the mean position, x is equal 0, it is x is equal plus a, and this is x is equal minus a. So these are the positions of the particle. Now we have to find the total energy at mean position. For the total energy at mean position, we can having total energy, it is equal PE plus KE. We have to find out potential energy at mean position and also kinetic energy at mean position. Similarly, the total energy in extreme point, it is potential energy at this point and also kinetic energy at this point. Similarly, total energy is equal PE plus KE here also. Okay. Now let us write the total. How we can find the total energy? We have to measure the potential energy and the kinetic energy of the oscillator. So let us find the potential energy of the simple harmonic oscillator. Then we have to find out at mean position and extreme position. Okay. So how we can derive the potential energy? Potential energy. Right. So here for a simple harmonic oscillator, so this is a pendulum, so which can be moving full aside x distance. Okay. So then for displace the x distance, there is some work done. So we have to using here some force. By the external forces, the displacement will be occurs. So here the work done should be done here. So how much work done should be here? The work done it is equal, W it is equal to minus F into X. Minus F into X. So this is the basic formula. So here in this case, for moving the particle from its mean position, the work done should be stored in the form of its potential energy. The work done, it is stored in the form of potential energy, that is U. U it is the potential energy. So for getting small displacement, so then dW it is equal to minus F into dx. So dx it is the small displacement, x it is the total displacement. For getting the total work done, so total work done we have to integrate on both sides. That is the dW it is equal to integral of dW from 0 to x, from 0 to x distance, and here minus of integral of 0 to x is f into dx. Okay, right. So from the f is equal kx here. F is equal kx. What is that here? F is equal minus kx. F is equal minus kx because of f proportional minus x. So f it is equal some constant minus into x. F is equal minus kx. We can write that f is replacing by minus kx. Minus into minus plus integral of 0 to x, where kx dx. It is equal, k should become outside of the integration and 0 to x. So we have to integrate the x. It is the x square by 2. So 0 to x. So this is the integral of x power n dx. It is equal to x power n plus 1 by n plus 1. So what we have to need? This is the capital W, where it is total work done should be in the form of potential energy. So from this we can write that it is equal to 1 by 2. So limits will be applicable where upper limit minus lower limit, x square by 2 minus 0. So 1 by 2 k into x square, 1 by 2 kx square. So this is the potential energy. So k it is nothing but what is k here? The constant it is nothing but from f is equal to ma we have to write that minus kx. Okay, a it is equal minus k by m x. Okay, from this you can write that a it is equal to minus omega square x to comparatively, where omega square is equal k by m. Omega square it is equal k by m, where k it is equal m omega square. K is equal m omega square. Let us write the where k it is replacing by m omega square. Then the potential energy U it is equal 1 by 2 m omega square a square. Sorry, that is x square. So this is the potential energy of a particle of a simple harmonic oscillator. What is the potential energy of the simple harmonic oscillator? Of m omega square x square. Of m omega square x square. Okay. How we can get that? The potential energy is nothing but the work done to move the particle from its mean position. The work done to move the particle from its mean position is stored in the form of the potential energy. So how much work done should be acting here? That is this much of work done. How we can find the K value? K, it is the m omega square. It is 1 by 2 m omega square x square. Okay, clear? So note it. Right. So here we have to find the potential energy of the particle, simple harmonic oscillator, and also at the main position and extreme position, Okay, it means right extreme, left extreme, in the positive x-axis and negative x-axis. So the basic potential energy PE is equal to 1 by 2 m omega square x square. This is the potential energy. At mean position, x is equal to 0. Therefore, potential energy PE is equal to 1 by 2 m omega square into 0 square. It is equal to 0. PE is equal to 0, that is the minimum. So, the potential energy at the mean position is 0. The potential energy at the mean position is 0. So, that you have to make one graph. So, this is the mean position. So, this is the particle which is, so this is the potential energy is 0. So, this is the mean position. And coming to the right extreme. So, here right extreme. What is right extreme here? X is equal plus A. Whereas PE is equal 1 by 2 m omega square, where x it is equal A square. Okay, so 1 by 2 m omega square A square. So this is the potential energy, whereas maximum. So at the right extreme, the potential energy PE is equal maximum value. It has 1 by 2 m omega square A square. 1 by 2 m omega square A square. Right. Now coming to the left extreme. Left extreme. So at left extreme, x is equal to minus A, where PE is equal to 1 by 2 m omega square, where x it is equal to minus A whole square. Minus A into minus A, that is plus A, it is plus A square, 1 by 2 m omega square A square. This is the potential energy. It is also maximum at the left extreme point. So this is the maximum. So PE is equal to 1 by 2 m omega square A square. So the potential energy is maximum at the extreme points, but minimum at the main position, it is nothing but 0. Okay. Now coming to the find kinetic energy of the particle. Kinetic energy. Okay. Right. So for getting the kinetic energy, the basic equation of the kinetic energy Ke is equal to 1 by 2 mv square. The velocity of the simple harmonic particle V is equal to omega into under root of A square minus x square. Already we derived it in our previous videos. Right. Simply we can substitute here 1 by 2 into m into, whereas V square it is nothing but omega into under root A square minus x square whole square, where it is 1 by 2 into m into omega square, whereas A square minus x square, square and root will be cancelled and omega whole square. So this is the kinetic energy of the particle. Okay, very important. So this is the potential energy of the particle. So this is the PE. Okay, so at extreme, so now we have to see at main position. At mean position, Ke is equal, at mean position, x is equal 0. Therefore, Ke is equal 1 by 2 m omega square A square minus 0 square. Therefore, it is equal 1 by 2 m omega square A square. 0 square nothing but 0. It is Ke is maximum. Where at mean position, kinetic energy is maximum. So one more graph we have to write here. So you should draw as like this. So this is the one more graph. So this is the mean position. So this is the kinetic energy graph. and this is the one of the extreme point, and this is the another extreme point here. Okay, so at mean position Ke is equal to maximum, that is equal 1 by 2 m omega square. What is that? A square. So now coming to the Ke at extreme. So this is the basic equation of the potential energy. So that is PE. Okay, now let us see. So Ke at extreme. So Ke at extreme, at right extreme, x is equal to plus A. So this is the x is equal plus A, where it is Ke is equal to 1 by 2 m omega square A square minus A square. X it is nothing but plus A here. Right, A square minus A square, it is equal 0. It is equal something into 0, nothing but Ke is equal to 0. So this is minimum. At where it is? It is at extreme point. So here Ke is equal. So this is the extreme where Ke is equal to 0. Okay. And now left extreme also Ke is 0. How it is? So the left extreme where x is equal to minus A. So then Ke is equal to 1 by 2 m omega square A square minus A square. So minus A whole square, it is equal plus A square. A square minus A square, it is equal 0. It is Ke is minimum. Ke minimum is equal 0 here. So here also Gn. Okay, what I am saying here it is, at main position we need to find potential energy, kinetic energy. At extreme potential point we need to find potential energy and kinetic energy. At extreme point we have to find potential energy and kinetic energy. The total energy at all the points remains same. Then we have to say the simple harmonic oscillator obeys the laws of conservation of energy. Law of conservation of energy. So at these 2 points, the total energy PE plus Ke, it is equal to half m omega square A square. It is Ke is equal to 0. At these 2 points, at mean position, the total energy of m omega square A square, because of potential energy, is 0. At this right side of the extreme point here, of m omega square A square. So here also the total energy is always remains same. Okay. So the equation of total energy, hence we can write that. So total energy is equal, Te is equal PE plus Ke here. Okay, so what is PE? So this is the potential energy, 1 by 2 m omega square A square. Sorry, x square. So that is x square. And plus what is kinetic energy? That is 1 by 2 m omega square A square minus x square. So from this we can write that 1 by 2 m omega square x square plus 1 by 2 m omega square. We have to multiply it by half m omega square A square minus half m omega square x square. So this minus and plus gets cancelled. It is 1 by 2 m omega square A square. So this is the total energy of the simple harmonic oscillator. This will be same at this point, this will be same, and this will be same. Okay, the total energy of the simple harmonic oscillator will remain always constant. Okay, so dear students, first 2 questions are very important. Definitely will asking in IPE examinations. So you will focus on these questions, and if you practice first 2 questions, you will get 1 question definitely in IPE examinations. If you like this video, please hit like and share to your friends, and you have to trying to follow our channel daily. And if you have any doubts, please ask me in the comment section. I will be provide or the material which I have. Okay, thank you one and all.